Well, hello and welcome. Today we need to talk about the classification of numbers. All right? And the objective here is to try to get you ready for this next exploration that we're going to be doing on rational numbers and terminating decimals. And so there's some things I want to make sure you know. And I'm suspecting there's a lot you know about how numbers are classified, but just in case, well, I want to just make sure that we're all starting at the same place. And so before I talk about numbers, let me take just a minute and talk about classification in general, because I think this is a fascinating topic. Whenever we begin to study something, we usually begin by classification. In the world of music, I start thinking about the notes, I give them names, I think about the chord structures, I give these chords names based on their characteristics, major and minor and augmented and diminished and all that kind of good stuff. In the world of geology, I love geology. We've got all these minerals, and these minerals are given names. They're classified based on their characteristics. How hard are they? What's their density, their specific gravity, what's their color, their crystal structure. And based on those characteristics, I give these different minerals names. In the world of biology, I've got my plant taxonomy book here, one of them. Here's kind of a cool plant. You probably can't see it very well there, but this is yarrow. Okay, and yarrow is classified in a certain family, in a certain genus, a certain species. It's a compositae. It's an Archilla milleforium is its genus and species, and all the plants are like that. And so I got books full of how to classify these things. Right, so I think this is true. You think about other topics as well, but oftentimes we start by classifying objects, and it's no different in mathematics. And so mathematics, we're going to start classifying the objects that we work with to begin with, at least one of the objects, which are numbers. Okay, so you might remember. I bet you remember. The counting numbers from a previous course. The counting numbers are, well, for example, when my children were little, they'd come to my office. I'm on the 3rd floor in the physical science building, and they'd climb the stairs. And what would they do? They would count the stairs. 1, 2, 3, 4, 5. Those are the counting numbers. And that's what we start with. And sometimes we include 0, sometimes we don't. Our textbook does not include 0 as a part of the definition of the natural numbers. Oftentimes we use an and to denote natural numbers. And sometimes we put a little subscript 0 there to denote natural numbers including 0. And so those are the counting numbers or the natural numbers. The integers are the natural numbers and the negative natural numbers and 0. And those are important numbers, and we denote those with a z. The z comes from the German word Zahlen, which stands for numbers in German. So in this class we're going to be studying mostly real numbers. Maybe a little bit later on in the course I'll say some things about complex numbers. We might take a brief look at complex numbers. But in general, we're going to be studying real numbers. And real numbers can be broken up into 2 parts. So if you throw me a real number, it's either rational or it's irrational. Those are the 2 basic subsets of real numbers. So for example, these counting numbers and these integers are both rational numbers. And so the question is, what is a rational number? Can we define it? And the answer is, sure. We give it a definition based on some of its characteristics. So we see a rational number is a number that can be written in the form of a fraction, a over b, where a and b are both integers. And so when you think about rational numbers, we often think about fractions, but they're special fractions. The fraction is composed only of integers. Right? Now this definition actually comes from the ancient Greeks, from the Pythagoreans. And they thought integers were pretty cool. And for a time they believed that all numbers could be written as the ratio of integers. And so they called them rational. Well, you may remember the Pythagorean theorem. And so if I look at like a square that's 1 by 1 and look at the diagonal of that square, I can use the Pythagorean theorem to find this distance, which ends up being the square root of 2. Now the Pythagoreans did a really interesting thing, which they were not very happy about in general, because they were able to show that the square root of 2 was not rational. And if you want to make me really happy, put a smile on my face, ask me about the proof for that sometime. I'd be delighted to show you. But again, I'd like to keep this video short, and so we're not going to do that. And so the square root of 2 is an example of a number that's not rational, a number that cannot be written as the ratio of 2 integers. Actually, it turns out that the square root of any prime number is irrational. So the square root of 5, the square root of 13, those are all irrational numbers. Pi is irrational. 3.1415 ... Okay, e, 2.71 ... It keeps going. And so these are some examples of irrational numbers that you may be familiar with. It turns out that there's a whole lot of rational numbers, but they're countable. I can count them. Like I can count the counting numbers, 1, 2, 3, 4, 5. I can count the rational numbers. The irrational numbers, are uncountable, which is kind of interesting. All right, so maybe that's enough of that. And so what we want to look at, if I think about a rational number, so for example, maybe 1/2. 1/2 is rational because it can be written as the ratio of two integers, the integers 1 and 2. And if you think about it, I can write 1/2 in lots of different ways. I can write 1/2 as 2/4, right, or 4/8, right? Oh, here's a special one. 5/10 is pretty special. I can write 1/2 as 5/10. That's another representation of 1/2. And because of our base 10 system, I can write this as 0.5. That's 5/10. And so I can write this 1/2 as a terminating decimal. I can represent 1/2 as a terminating decimal. It's a fraction that, if you will, terminates when I think about its decimal form. I can also write 1/2 as 50 or 100. Well, that's 0.50, which is the same thing. It's 1/2. This is 50 100ths, which is the same as 5/10. But the point is that it terminates. And so the question is, under what conditions do these fractions terminate, and when do they not terminate? And so, for example, if I look at like 1/3, 1/3 is a fraction, and if I look at it's rational, right? It's the ratio of integers. 1 and 3 are integers, so it's a rational number. But when I think about how it's written in decimal form, if I do the long division or whatever, I can find out that this is 0.3333333, and it keeps going. It doesn't terminate. It repeats. And sometimes we write that as 0.3 with a bar on top, and that bar means that the 3 is repeating, right? And so the question for this first exploration is going to be, can I take a look at some of these numbers, and can I explore these numbers? Can I determine under what conditions do they terminate, and under what conditions do they repeat? And so that's what we're going to be doing next. And so I hope this helped. As always, if you have questions, please ask. Make sure you read the book. You need to read the book. You need to read the section. But ask questions about things you're having troubles with. And I hope you enjoy learning about the classification of numbers. And I hope you really enjoy this next exploration that we're going to do. Thanks.